So in the previous video, we went over the example of IQ of IB students, and we produced a Frequentist P value. And in this video, primary thing we're going to do is use the Bayesian approach to look at the same issue. Also, two other goals. One is to, again, see some more run-jags code, and then see in particular how run-jags can create derived values or derived variables. We'll begin with our directed acyclic graph. And as always, we'll begin at the bottom with the likelihood that reflects the process that gives rise to the data. So the data are going to consist of these 9 values of y, which are the 9 IQ values. They're deemed to arise from a normal distribution, and that normal distribution is going to have a mean mu, and that's the thing we're really going to focus on, and it's going to have a precision of 1 divided by 225. Where does that come from? We're assuming that the standard deviation of this normal distribution is 15, which means it has a variance of 225, and in run-jags, the normal distribution is parameterized with precision, which is tau, which is 1 over sigma squared, which is where we get this 1 over 225. We need to specify a prior value for mu. There's our prior. It's going to be a flat prior. It's also going to be a normal distribution. It's going to have a very low level of precision. So if this is our precision, then the standard deviation is going to be 100. So it's going to be a flat prior. I'm going to specify a value of mu of 115, but given the flatness of this prior, it doesn't really matter what's going to be specified as the mean. And then, interestingly, we've got this new thing, which is a derived value. And I've indicated it's a derived value by the dashed line. It's going to be an equal sign because the value is going to be determined deterministically. And there is the value that we're going to create, this thing called prob, that's going to be calculated via the step function. So how does the step function work? So the step function is going to work on some argument y, and it's going to return a value of 1 if y is greater than or equal to 0, and a value of 0 if y is less than 0. So you think what's going to happen as run-jags goes on its random walk, it's going to go, and we're going to see it's going to go through 60,000 iterations, and at each iteration, it's going to calculate a value of mu, but at each iteration, it's also going to calculate this derived value of prob that's given by that formula. So you think what's going to happen if the value of mu is less than 100, let's say it's 95, then what's going to be returned is a value of 1, whereas in contrast, if mu is greater than 100, let's say it's 105, then what's going to be returned is 0. So what we're going to get after 60,000 iterations is there going to be 60,000 values that's going to be either 1 or a 0. If we take the mean of these 60,000 ones or zeros, that's going to give us the proportion of values that are ones. That's going to give us the proportion of instances in which mu was less than or equal to 100. In terms of data preparation, we're going to have an Excel spreadsheet called IQ CSV, again, CSV extension. We're going to read it in using the read CSV function, and there's the name of the file there. We're going to make a data frame of it. We're going to look at that data frame, and we can see that it's really going to just consist of this one variable y and 9 observations, the 9 IQs of the 9 IB students. We do some more preparation. We create an object y, which is just equal to these 9 values. We create another variable called knobs, which is the length of y, which is going to be the value of 9. And then we create a list using the list function that I'm going to call data file that says that y is going to be equal to y. So y is going to be equal to these 9 values, and knobs is going to be equal to the integer 9. If we look at the structure of this thing called data file, we'll see, in fact, that it is a list, and it contains these 2 items. First is y, the 9 IQs of the students. Secondly is this integer 9, the number of students. So we've got this list called data file. So we're going to start off with this list called data file. We're going to operate on it with the dump format function, and that's going to create this object called data for jags, which is going to be in a format that run-jags can understand. So let's come down to our model statement and just point out that, there's our model statement there. But one of the real big advantages of doing a directed acyclic graph is that if you do this correctly, then creating the model statement is pretty easy, because each one of these arrows is going to have a statement in the model function. And that statement in the model function is going to be accompanied by either a tilde or an equal sign, depending on whether the value is derived from a distribution or is derived, in this case, with an equal sign deterministically. So there's our model statement. Think about the likelihood function. So we're going to have a loop. And what we're going to do is we're going to loop over I from 1 to 9. So what we're going to do is we're going to loop over these 9 values of y. So y from y1 to y9, y1 to y9. We're going to loop over those values, and each one of those in turn is going to be assumed to have been arisen from a normal distribution with mean mu and standard deviation 1 over 225. So that's our likelihood function. Then we have our priors. As mentioned before, our prior value for mu is assumed to arise from a flat normal distribution with very low precision. Doesn't really matter what we choose as our mean here, because it is going to be a flat distribution. And then finally, we've got this thing called prob. And prob is going to be given to us by the step function. And so again, if you think what's going to happen, we're going to have these 60,000 values of 1 or 0, depending on whether mu is less than, equal to, or greater than 100. And then the average of all these is going to give us the proportion of instances in which mu was less than or equal to 100. What are we going to monitor? We're going to monitor mu. We're obviously interested in that. We're going to monitor prob, or derived. We're going to have 3 chains and 20,000 observations each. And when we run the analysis, what we get is actually very gratifying, because the mean we get of mu, 110.98, is almost exactly the same as the observed mean of 111. And then we've got this value of prob, which is 0.0139. And again, to reiterate, that what that means is that if we look at these 60,000 values that were generated by the step function, that in 0.0139 proportion of the cases, the value of mu was less than or equal to 100. And this value here is exactly the same as the p-value that we got from the frequentist approach. So this is how you do the Bayesian posterior. And in the next slide, we're going to follow up in a more direct comparison, explicit comparison of the frequentist versus the Bayesian approaches for this IQ example.